So if the equation of exponential growth is not accurate to model an actual population, then what is a good model? So you can think of, for example, this beautiful spider. It is called golden silk orb weaver. There is a subspecies found that you can find in Singapore. They're very, very pretty, really. So females are very large. Leg spread can be like 30 centimeters or even 50 centimeters, and the body can be probably up to 10 centimeters. So you can find them in national parks. So they are all sorts of colors, very bright colors like yellow and blue. They're really beautiful. Why am I talking about spiders? Is because, as far to my knowledge, or at least it probably was true a few years ago, is that the spider is capable of making very strong web. So I have even heard that among materials known to the mankind, only Kevlar is stronger than the web of this golden silk orb weaver. So, and since, this material is so strong and so precious, there were attempts to grow these spiders commercially. If you have a huge farm of spiders, like they have farms of silkworms, then they could make, probably arm vests or all sorts of stuff out of this web. Well, but unfortunately, these attempts to grow golden silk orb weavers commercially, they failed. And you know why? Because the spiders, if there are too many of them in one place, they start eating each other. Okay? So, if they have plenty of resources, then they multiply quickly and they experience exponential growth. But once there is not enough room for them, then they just start eating each other. So, and that's how they compete for resources. Well, and the correspondent model should somehow reflect the fact that they are competing, right? So notice something interesting, that in this logistic model, we can rewrite it. So we can write that this is R, Y, and this term tells us that the growth rate of the spider population is proportional to the population itself. But then minus what do I have to subtract? R over K times Y squared. So I will write A times Y squared. So minus some coefficient times Y squared. But if Y is population, then the square of Y is proportional to the number of pairs of spiders, right? So if Y is the number of spiders, then Y squared is, well, it's not exactly, but it's proportional to the number of pairs of spiders, all right? And by subtracting this, what we are claiming is that the more pairs of spiders there are, the slower is the growth rate. So which means that more different pairs of spiders, they slow down the growth rate, which is what happens in practice. All right, so let us review. Here is the logistic differential equation. And the basic logic here, so that there are two constants here, R and K. The idea is that if the population Y is small, is much smaller than K, which is called the carrying capacity, then Y over K is almost zero, which means we can neglect the terms Y over K, and the rest is just the exponential growth. But if Y is growing, then eventually it's going to approach K, and then Y over K is going to be almost 1, and then dy dt is going to be almost 0, and then we get no growth. So, and no growth means that the population becomes constant and it stabilizes. Alright, so here y equals 0 and y equals k are equilibrium solutions. And the constants r is called the intrinsic growth rate and k is called the carrying capacity. Right, so please remember these terms: intrinsic growth rate and the carrying capacity. So here is an example. So we can easily extract the carrying capacity from the plot. And so remember that y equals 0 and y equals k are always equilibrium solutions. So while y equals 0 is probably not very interesting, it's going to appear in all sorts of diagrams with a logistic differential equation, but carrying capacity, so here is an equilibrium solution, y equals 2, and y equals 1.4 is an equilibrium solution here. So you can always find the carrying capacity of a logistic differential equation by just looking at the direction field. Intrinsic growth rate, well, it's kind of harder to find. So roughly speaking, what is going to happen is that if, say, instead of this equation, you consider something like, so imagine that you, I don't know, multiply the intrinsic growth rate by, say, 10. Instead of this equation, you took 15y times 1 minus y over 2. This would mean that positivity and negativity of the y component of all the arrows would remain the same, but they would become much steeper. So these arrows would kind of look upward instead of upward and a little bit to the right. And so the slope would be 10 times more steep. Here is a little problem for you. I suggest that you try to solve it and post your solutions into YouTube as comments to this video, and I will look on them and tell you if it's correct or not. Right, so show that the general solution of the logistic equation is like this. And finally,